everyone. Today we're going to continue our discussion of Module 6. So we're in Chapter 9. And we're going to discuss electrolytes and non-electrolytes. So electrolytes are really important for our body to function. These are things such as sodium ions, potassium ions, chloride ions, and bicarbonate ions. So our cells and our organs need these types of ions in order to properly function. Now, previously we did talk a little bit about Gatorade as an example of a beverage that has a lot of electrolytes in it. And if you look at the label on a bottle of Gatorade, you'll see that there are, for instance, different ionic compounds like sodium phosphate or, similar compounds. And those are compounds that will dissociate in solution and produce positive and negative ions, or electrolytes. So in chemistry, we think of strong electrolytes as those that dissociate 100% in water. So they'll produce positive and negative ions. And they'll also form solutions that conduct an electric current strong enough to light a bulb. So down below we have an equation for sodium chloride, and it's dissolved in water. So initially the sodium chloride is a solid, but once it's added to water, it's going to completely dissociate into its individual ions. So the sodium ion and the chloride ion. Now, the way that we can test how strong the electrolyte is by using a simple light bulb setup here. So we have a light bulb, and it's connected to two electrodes that are placed in a saltwater solution. So those electrodes are shown there and there. And one electrode is negatively charged, so that's the anode, and one is positively charged, so that's the cathode. And when we have freely floating ions in solution, the positive ions are going to be attracted to the negative electrode, and the negative ions will be attracted to the positive electrode. And this is going to encourage a current to form, and that can light up the light bulb. Now, weak electrolytes only dissociate slightly in water. And they'll form a solution with a few ions, but mostly undissociated molecules. And down below, we have a really good example of a weak electrolyte, and that is hydrofluoric acid. So hydrofluoric acid doesn't completely dissociate in water. It only partially dissociates. So you will end up with a few hydrogen ions and a few fluoride ions in solution, but we're going to mostly have the original molecule. So you'll notice here we have double arrows. So what the double arrows indicate is that we do have some dissociation of ions, but those ions can actually reattach to each other or reform their bond and give us back the original molecule, which is hydrofluoric acid. So in our solution, again, we would see some individual ions, but we would mostly see intact molecules. Now, because we do have a few ions floating around, we can still generate a current in this solution. So we'll see the light bulb kind of light up, but it's not going to be as bright as in our previous example where we had a strong electrolyte that completely dissociated. So weak electrolytes are kind of the in-between form of these electrolytes and non-electrolytes. All right, So the last category is non-electrolytes. So non-electrolytes, you can probably guess, they do not produce ions in water. They do dissolve in water, so maybe they're polar molecules. However, they're not going to produce any ions, and therefore they're not going to conduct an electric current. So one really good example is methanol, which has the chemical formula CH4O, or sometimes it's written as CH3OH, and the OH tells us that we have a polar bond. So that's why methanol does dissolve in water, because remember, like dissolves like. However, we're not producing any ions when we dissolve methanol in water. So we're just going to end up with an aqueous solution of methanol. And off to the right, you can see this in our figure too. These molecules are all intact. They haven't dissociated into any ions. So that means they're not going to really be attracted to one electrode or the other. And so we're not going to see any current generated, and our light bulb will remain unlit. All right. So let's do a quick learning check. Let's complete each of the following equations for strong electrolytes in water. So remember, strong electrolytes dissociate completely in water. So if you want to try this on your own first, see if you can figure out what the products would be after these strong electrolytes dissociate. And then you can unpause the video and we'll go over them together. Okay, let's go over number 1. We have calcium chloride, and we were told that this is a strong electrolyte, so that means it's going to completely dissociate in water. So would our product be A, B, or C? So looking at A, we already know that this is wrong, right? Because calcium chloride is a strong electrolyte, so it should dissociate. It's not just going to stay the same. Now in B, we do have ions present. Okay, and in C, we also have ions present. So B and C are good contenders for the right answer. Now looking at B, we have the calcium ion, and then we have this Cl2 minus. Okay. In C, we also have the calcium, the calcium ion, and then we have 2 chloride ions. So that's really the only difference between B and C is those chlorine ions. Okay, so Cl2 is actually neutral. It doesn't typically have a negative charge on it. This is one of our diatomic molecules. So that's probably not correct. And in fact, C is the correct answer, because when calcium chloride dissociates, we do end up with the calcium ion and 2 negatively charged chloride ions. Now, the other problem with B is that we have just 1 negative charge on that chlorine molecule, but we have a 2+ charge on calcium. So those don't even balance each other out. So B is definitely wrong. Okay, so we would end up with calcium 2+, which is aqueous, and 2 chloride ions, which are also aqueous. All right, let's look at number 2. We have potassium phosphate. And we're also told this is a strong electrolyte, so we know that it will completely dissociate in water. Now, we can already eliminate one of our answers because remember, we know this will dissociate into ions. So B is not correct. Okay, so now we're left with A and C. And Looking at A, we have 3 potassium ions and 1 phosphate ion. Okay, seems reasonable. Let's look at C. We have K3 plus, and then we have P3 minus and O4 minus. Okay, so let's see. Now, potassium ions, they're not really going to form a molecular compound like that with K3. But additionally, if we look at all of these charges, they don't balance each other out. We don't end up with a neutral molecule. So C is not correct. That's just definitely false. All right, so A is our answer. We would end up with 3 potassium ions and 1 phosphate ion. So we would get 3K plus aqueous plus a phosphate ion. Now, one more reason that C is not correct is our phosphate ion is not going to break up into individual potassium and oxygen atoms. Remember, in a polyatomic ion, we have covalent bonds holding those atoms together, and then they just have an overall charge. So it would be really difficult to break up the phosphorus and oxygen atoms from each other. Okay, so hopefully that helps a little bit with kind of figuring out what type of ions we would end up with in solution for strong electrolytes. And there are the answers. And let's do one more practice problem. Let's write the equation for the formation of a solution for each of the following. So A, we're going to write an equation for the dissociation of potassium chromate, a strong electrolyte in water. So in that molecule or compound, we have potassium, and then we also have the polyatomic ion chromate, which is CrO4. And I don't think we've seen that before, but just so you're aware that that's a polyatomic ion. In B, we're going to write the equation for the partial dissociation of the weak electrolyte, phosphoric acid, in water. And then in C, we're going to write the equation for the dissolving of the solid sugar, C12H22O11, in water. And I'll give you a hint. Sugar is a non-electrolyte. Now, if you want to try this on your own first, feel free to pause the video, and then when you unpause, we'll go over it together. Okay, let's go over A. So we're told that potassium chromate is a strong electrolyte. Okay, so we already know that this will completely dissociate. All right, so I'm showing that the solid potassium chromate is added to water. And let's do the easy part. Let's figure out how many potassium ions we'll have in solution. So it looks like we'll end up with 2 potassium ions, and those will be aqueous after they're dissolved. And then we end up with the polyatomic ion chromate, CrO4. But what is the charge on chromate? So we have 2 positively charged ions, the potassium ions, and we know that the chromate ion has to balance that charge. So what should the charge on chromate be? 2 minus, or minus 2. All right. Okay, so that would be our dissociation of potassium chromate. Now, let's write out the partial dissociation of the weak electrolyte phosphoric acid in water. So H3PO4. Okay, so this is one of our acids, and the reason I know that is because there's a polyatomic ion attached to hydrogen ions. And they are covalently bound. They're not really an ionic compound there, but we do happen to have a polyatomic ion present. Acids are kind of strange in that way. But let's show that this is partially dissociating. All right, so typically acids are present in an aqueous solution. Now, if this is going to partially dissociate, we want to show a double arrow. Because remember, weak electrolytes will form some ions, but those ions can recombine to form the original molecule. All right, so this is in water. Okay, so there's a couple different ways you could write this. Now, acids usually only give up one hydrogen at a time, so you could write this as H plus whatever's left over, which would be H2PO4, and then the charge would be -1 because it is giving up a positive ion. So we'd have a negative charge left over. So that's one way to write this. The other way is you could show that we're forming multiple hydrogen ions in solution. So what we would do there, let me just erase that. So what we could show is that eventually we would end up with 3 hydrogen ions and then 1 phosphate ion, which would have what charge? So if we have 3 positive charges from hydrogen, what is the charge on phosphate? 3 minus. So that's another way to show the dissociation of that weak electrolyte. As long as you're showing the double arrows, that's fine for now. When you get into general chemistry, you'll learn more about acids that have multiple hydrogens attached. And again, you'll learn that only one hydrogen is released at a time. And once you lose the first hydrogen, it's really hard to lose the 2 other hydrogens in this case. But, you know, we haven't gotten that far yet, so don't worry too much about it. Okay, so now for C, sugar. If we dissolve sugar in water, what happens? So I gave you a hint that sugar is a non-electrolyte. So if we start with the solid and we dissolve it in water, what will happen? Nothing, right? It's just going to still remain as sugar. It's not going to dissociate. The only difference is that we will have an aqueous solution of sugar instead of just the solid sugar. All right. And here are the answers if you need those later. Now, next time, we're going to talk about something called a concentration. So we're going to figure out if we have a certain amount of solute in a certain amount of solvent, how can we express that? And we're going to use concentrations to express that. So we'll talk about that in the next video.